Okay, I am recording now, and I think everybody's mostly here. Okay. All right. And wait a sec. Sorry. Okay. Sorry. And you can, yeah, you see my screen. Yeah. Okay. Keeps. There's usually a green box around it, but it's not showing it. Okay. So, welcome to Sociology 101. Just kidding. This is Organic 2, Chem335. And I'm going to go through the syllabus, and then I'm going to go through a couple of the different, a little bit of review material. And then we're going to jump into the first chapter, which is the NMR chapter. Okay, 1 second, sorry. Okay, there we are. Okay, yeah, so this is Organic 2, Chem335. My email address is up top, marksfsu.edu. It's really easy to reach me. First couple weeks or so, we're going to be synchronous, kind of like this on Zoom. And then we are going to, and the normal times are Tuesday and Thursday, 5 to 6:15. Once we get rolling though, I basically convert the course into asynchronous. And so the idea is you're going to get the same kind of lecture content, but it will be on Tuesdays and Thursdays, but it's going to be posted on YouTube or iLearn, and is the quality of the videos is really good, and you can get everything out of it. Now, if you need personal interaction, the office hours are a great way to do that. And I try to record the office hours as much as I can. So if you can't make it, you can still watch the office hours. And we have these weekly quizzes, and the office hours really help. You know, a lot of students come and ask good questions that might help you out on the quizzes. Okay. And the office hours, the way I designed them, Monday, Tuesday, and Friday, sounds kind of weird, I guess. But the quizzes are all going to be on Tuesdays, Tuesday 5 p.m. basically. So by having office hours on Monday, Tuesday, and Friday, it kind of gets you ready for the quizzes. That's kind of the point of these office hours, right? Okay. In addition to iLearn, which we use, I also have a course website. I would make a bookmark to it. It's all set up already. I'll show what that looks like. Here it is. So there's a publicly accessible website. You don't need a password. It's not, it's just, we have a lot of material in this course, and having everything on iLearn is almost like overwhelming. So I break it up a bit, and this public website has stuff like the homework assignments and reading assignments, lecture notes, etc. So for example, we're going to start with chapter 10, the NMR chapter. And so this has like some kind of reading assignments, and chapter 10 is heavily PowerPoint. So there's PowerPoint, these part 1 through 7 are all parts PowerPoint. Yeah. And now when I say parts 1 through 7, it's not like those are 7 lectures. Some of the parts are like 3 or 4 slides. So this is just a good organization for this chapter. All right. But anyway, my point is that there is this other website that is public. You don't need a password. Make a bookmark to it. This is also where the syllabus is. The syllabus is up top left, and a couple other things that may be helpful to you. All right. So that is the publicly accessible website. Any questions yet? Okay. All right. So that's that. Prereq, you need to have passed Organic 1. I've pretty much have filtered people out that have tried not to have passed Organic 1. Our textbook is Volhart and Shore 7th edition. Now, 6th edition will work. It's actually almost hard to get the 6th edition. In reality, 6th edition, 7th edition, they're all the same basically. But the key is the authors. And, you know, being able to do the homework will really help you out on the quizzes. So I just looked on Amazon, and you can buy it used for $25. You can find these online. There's other ways to find them. I think I even looked on, what was it, eBay, $4 right there. So this is the book for $4. So somebody can bid on it if you're an eBay person. They get you on shipping. Okay. Anyway, yeah, so that's the book. We follow the book to the letter. It's really good to have the book. You know, the lectures are pretty good, but here and there, it might be helpful to, you know, have another perspective. And you know, I'm going right out of the book. So, also for the homework is a great thing to practice with. It's a really good book. I say optionally organic molecular model kit. You don't really need models for organic 2. We have lots of difficult things that don't necessarily involve models. So I wouldn't really be worried about the models. There's also another book called Organic Chemistry, Second Language, Second Semester Topics. That's actually pretty good. It goes over some of the mechanisms and kind of complex stuff that we're going to be talking about. I would say, you know, if you don't have this book and the study guide, I would try to get that. There's a couple ways to get it. All right. Okay, so for the most part, like I said, Zoom lectures for the first couple weeks, just to get us going. And then we're going to switch to an asynchronous mode where yeah, two lectures a week, and you can watch them whenever you want. Some people like to watch them all on Saturday night, or you know, kind of whenever you want. Just don't get behind, you know. And I would recommend, you know, when I post them, try to watch them pretty soon, you know, that day or something, just so you don't get behind, because it is easy to get behind. It's a really hard class. I have an iLearn site, the iLearn site, as well as a YouTube channel called MXASFSU. I actually have a lot of the Organic 2 from from the spring already up there. I might delete it all just so you guys don't get confused. It might just help for us just keep, you know, start from scratch. Okay. And after a couple of weeks, weekly quizzes during normal class time. All right. And I'm going to announce this. The first quiz is probably going to be like next Tuesday, and we're still doing Zoom at that point. The first quiz is just a warm-up quiz. It's going to be like, you know, like Wikipedia search a molecule and draw it. That'll be the first quiz, and that won't be timed. You'll have like several days to do this first quiz. All right. Once we get going, though, you know, in the course, quizzes are going to be Tuesdays during the normal lecture time, and you know, that's when we're asynchronous, right? Okay. So what else? We don't really have exams. We just have a whole bunch of these quizzes. Okay, so you know, some people want exams. You might be one of those crazy people that just loves exams. Well, you're not going to get exams. You're going to basically get a whole bunch of these open note quizzes every Tuesday after a couple weeks, and they're going to be normal class time. If you have another commitment during this time, you won't be able to do the course. You can't. So if you're planning to, like, if you got to work on Tuesdays from 5 to 6:15, it's not going to work out. You'll probably have to leave this course. You really need to be accessible during those times. All right. They won't always take the full time period. There's going to be a time limit. And the other thing is, most of the quizzes will be over the last week, so you kind of know what to study, and I give you some hints on, you know, what needs to what you got to look over, and maybe some homework problems that'll help you out. Okay, so the quiz is on Tuesday. It'll usually cover the previous Tuesday, Thursday lectures. First couple of quizzes, I'm going to be very clear on what the topics are. Okay. Okay. There might be a couple of participation points for the first couple lectures when we're doing the Zoom stuff. All right. No quizzes are going to be dropped. The reason is because we have so many of these quizzes, so a single quiz won't destroy your grade. The other thing is they're all open note, so they should be all pretty doable. You know, I tell you what they're going to be on. And the other thing is they all vary in number of points, so it's kind of hard for me to say, oh, let's drop the lowest point quiz, you know. It just doesn't make sense. So we're all on even ground and no quizzes are going to be dropped, all right? But you have a lot of opportunities to get points in this course. And there's these 2 super quizzes. Super quizzes are you know, there's ones in the middle of the course, ones at the final, basically. And those are a little more cumulative, all right? Okay, then I have this really silly concept called magic word. So there's no magic to learning organic chemistry, it's a ton of hard work. Here and there, though, we're gonna have the magic word associated with a concept in a lecture, okay? And this is to make sure you guys are actually watching the lectures, okay? So, and then on the quiz, I'm gonna say, what's the magic word? And you're gonna have to say what the magic word is. So you gotta watch the lectures, all right? So when we talk about base-mediated intramolecular aldol condensation, the magic word might be hamster. And then you gotta write hamster, okay? And there's gonna be a point deduction if you don't do that. Okay, so, you know, I'm not going to do this very often, but here and there. So just keep your ears open. And when I tell you a magic word, you might highlight it in your notes. So you know, oh, this is the magic word. And the other thing is you really need to take notes. So you're going to be taking tons of notes and be ready for tons of notes. Some of it's PowerPoint, but most of this course is just a bunch of note taking. All right. Okay. Assigned homework. Okay, so like I said, a subset of the textbook problems will be on the course website. I already showed you that. It's on the public website. Do as many as you can. It'll keep you on top of everything. Most likely, if you do all the homework, you're gonna get an A in the course. That's pretty much, if you want an A, that's a way to do it. You don't need to do the homework to get an A, but certainly doing the assigned homework will help. And the other thing is, by doing the homework, you know, you might get stuck, and then that's a reason to come to office hours, and then we can talk about problem type, right? So the assigned homework will really just benefit you. Okay, you're not required to do it, and I don't grade you on the homework. I don't check that you do it, but the good students are doing homework. That's pretty much it. And, you know, it also, if you need to take MCATs and GREs and stuff, if you don't know this material, you might still be able to kind of pass the course, but you are going to get destroyed when you need it for like a GRE or MCAT, right? So the homework is going to help you. All right. So like I said, there's a course website. This is the publicly available website, reading assignments, subjective homework problems, figures, resources, PowerPoints, all that kind of stuff. iLearn is also available, and that's where I post some other things on there, including the video lectures. The video lectures are also over on that YouTube site that I mentioned. But yeah, you'll get used to these 2 resources and, you know, what's on which, okay? First couple of weeks are synchronous, like I said, the YouTube channel, good. Or you can watch them on iLearn. You don't have to use YouTube. Whatever works better on your computer or tablet or whatever you're using. Watch them at your own convenience, take notes like in a normal course. They'll be critical for the quizzes and the super quizzes. Generally speaking, for letters of rec, you need to get a B in the course, miss no more than a weekly quiz, and I have a little bit of flexibility on that. This isn't really a PowerPoint course. A lot of the way I'm doing this course will be with a little camcorder. And that's, you know, you'll see it. It looks like a whiteboard. It's kind of like you're in the class. And I think that it works really good because this class is really hard and you need to copy everything that I'm copying down. Okay, so there's gonna be a little bit of PowerPoint, but it's mostly not PowerPoint. Okay, so yeah, I'm gonna use this. Well, okay, so yeah, you're gonna have two note-taking styles. Annotating like PowerPoints, and I give you PowerPoints, you can annotate them somehow, print them, do what you need. And the other thing is kind of a whiteboard style where you're just going to copy everything I do. And you know, if you get stuck, you have to ask questions and take notes on paper, iPad, whatever. Okay. There's no extra credit as such unless I give it to you. And, you know, I think the most common thing is at the end of the course, somebody's like, oh, I just need extra credit. I don't know. You know, I don't do that unless it's applied to everybody. And so I give everybody some extra credit here and there or opportunities, but you can't just say, oh, I want to do an essay on benzene or something. We don't have that. Okay, and here's the grading scale. And we're far away from the grading scale. Other things, go to each of the lectures virtually or, you know, watch the asynchronous lectures. Read the textbook, do the homework problems. I recommend somehow combining your lecture notes and textbook readings if you can, and then kind of recopy your lecture notes. That would be the best way to do this. Alternatively, just recopying your notes is a useful thing. Now with the YouTube type of things, you can kind of just take your notes kind of slowly and carefully and, you know, pause the videos. So you might be able to make a really good notes like in the first pass, like, you know what I'm saying? Like in a normal class, in a normal classroom, I absolutely recommend everybody should recopy their notes. But this is not a normal classroom. So doesn't, you know, but the point is that recopying your notes does help you and absorb the material. Okay. Anyway, so these are just a couple ideas. And having recopied notes that look really nice will help you when you're taking your GREs and MCATs and stuff like that. Index cards are actually a pretty cool thing. I used to be skeptical of index cards. The point of an index card would be like you have a reaction. We're going to learn 1,000 reactions in this course. Not 1,000, but a lot, you know. And you need to know the mechanisms. You need to know the reagents. You need to know some examples. And an index card can sufficiently summarize that. I recommend copy the reaction, the reagents, maybe examples on one side, and a detailed mechanism on the other. Because I'm going to ask you for both of those types of things. Having the index cards will help you. It's open notes. So this is, you know, everybody should get an A in this course, right? Okay, yeah. So then attach a paper clip maybe around a group of index cards that have a similar mechanism. That might help. There's also some apps. I'm not really paying attention to the apps, but there are some. Khan Academy is pretty cool. People like that as an organic chemistry study tool. Okay, here's the schedule. So we start with, there's a question?
Getting into my class.
Oh, sure.
Yeah.
Oh,
Okay, so you take this with you? Okay. Let me just take a quick photo of it.
Mute.
I'll get the schedule with the tallies.
Is somebody talking? Hello, hello. Okay. Is there somebody with their hand up? I'm looking.
50. I'll lay down Pasha. The gloves can be.
Wait, one sec. Sorry. Was there a question? Okay. One second, sorry. Okay. All right. So yeah, we're starting on chapter 10, which is the NMR chapter. And then we're going to go into the alkyne chapter, chapter 13. From there, we go into the aromatic chapter, so benzenes and things like that. And there's some, chapter 16 is another aromatic chapter, the synthesis of aromatic compounds. And chapter 17 are carbonyls, so ketones and aldehydes. They have a whole bunch of reactions and reactivity. And chapter 18 is, you know, some of these words you don't even know yet. Enol and aldol, it's a whole class of reactions. We're gonna have our super quiz on the 9th of March, super quiz number 1. Then we're gonna get into chapter 19, which is carboxylic acids. We have a couple of these buffer days, which is just like if we get behind, we just use the buffer day. I'm always gonna have 2 lectures a week though, aside from spring break, okay? Chapter 19, carboxylic acids. Chapter 20 are carboxylic acid derivatives, and it's just like variations on the theme of carboxylic acids. 21 is amines, so nitrogen, you know, like a NH2, carbon with NH2 on it, things like that. Aryl substitution, these are just kind of like advanced topics. We'll get there. Don't be too worried yet. And then ester enol reactions. Okay, 1 second. Okay, cool. What else? Academic honesty policy. So it's important that everything's done by yourself. You're not in consultation with other students or websites. Now, using a resource like for your studying is okay. The problem is cheating, I guess. And so if you're, you know, there's various ways to cheat in these kind of online modalities, and I'm pretty aware of these methods. I'm kind of keeping track of them. I'm pretty I pretty much don't have any tolerance for this, and so if you get caught, you're going to be punished as best as I can possibly punish you. Not to be mean about this, but it's been an issue for a couple semesters, and we would probably aim to even record this on your transcript. All right, so you got to just keep that in mind. I've been doing this. Isn't my first course I've taught. I've been doing this for about 15 years, and I've actually caught a lot of students doing this. I actually this really started in the spring, you know, and when COVID started, and there was a website that was a lot of students were using, and I actually became an employee of that website. So I'm still part-time, you know, an employee there. So keep that in mind, I guess. Okay, with open note quizzes, there's no excuse to cheat. Don't even be tempted, because you know, the other thing about this is it may work for you. You might actually successfully cheat, and you know, you might cheat a couple times, but it may catch you later and then figure out, oh, they cheated on these other quizzes. So sometimes it haunts you later. So yeah, it might work early on, and then later I'll actually be able to figure out, oh, this person was cheating, and then anyway. So keep that in mind. All right. If you're a DPRC student, you get extra time on the quizzes, and contact me or contact the DPRC office about that. And we have SFSU has a policy against sexual violence, and there's some information here and a phone number. All right. Oh yeah, we do have a list of student learning outcomes that are on the department website. Okay, all right, so we are good here, and let's get going. Okay, so you all see this. Concepts you absolutely must have learned from Organic 1. All right, so this course is cumulative, and we build on Organic 1. So you need to have certain concepts down, and if you don't have these concepts down, it's really going to hurt you, okay? If you get behind in this course early on, it's kind of hard to catch up. All right, so what are the concepts that you absolutely must have learned from Organic 1? Well, first of all, this is the book, 7th edition, Volhart and Shore. 6th edition is pretty similar. You could probably get away with the 6th edition. The 8th edition's out too, but it's really expensive. That's why we use the 7th edition. And then there's also the McMurray book. You know, most students are not using that. We did transition from McMurray a while ago, and I don't think anybody's using McMurray anymore. So if you are, yeah, well, anyway, so you should really have the top one, Volhart and Shore 7th. Okay, old reactions. So you do need to know certain old reactions, reagents, the regiochemistry. Remember the Markovnikov and anti-Markovnikov? You need to be familiar. You don't need detailed, you know, every little detail, but there's certain things you need to know because we're going to build on them, right? I won't explicitly test you on the mechanism of old reactions because I'm going to be testing you on the mechanism of new reactions. But we were going to build on these old reactions, so you got to know them. Okay, so among what I'm going to talk about, the most important stuff has some stars. This is all on the website too, so you can go through this later too. But yeah, like oxidation or reduction, this is a big thing. The idea of taking primary alcohol and being able to oxidize it to an aldehyde and then to a carboxylic acid. So this is all Organic 1 stuff. PCC is kind of like the standard oxidizing agent you would use to go from alcohol to an aldehyde. If you want to go further, you can go with CrO3 and acid. If you want to go from the primary alcohol all the way to the carboxylic acid, you can do that in one step also, okay? Okay, And if you have a secondary alcohol, you can oxidize that to the ketone with PCC. So PCC is a chromium-based oxidizing agent. And I should also mention that you can do, going from left to right, you're doing oxidation. Going right to left, you're doing a reduction. So sodium borohydride is, one way to do that. You could either do that on a ketone to make an alcohol, or the aldehyde, you can go back down to a primary alcohol. So sodium borohydride, NaBH4, is the way to do that. You haven't learned this one yet, but carboxylic acid to primary alcohol is carboxylic acid to primary alcohol can be done with this more intense reducing agent called lithium aluminum hydride. Okay, all right, let's see what else. Okay, so other, reductions, I guess. You learned this in chapter 12, catalytic hydrogenation of an alkene. So it's basically, you're adding H2, right? Both of these are CHs, and you're adding a pair of H's, so you get CH2, CH2. That's one of the reactions from chapter 12, catalytic hydrogenation. Then you have the idea of, like, if you want to go back and forth between an alkane and an alkene, you can do that, right? So from an alkane, which doesn't have very much reactivity, in chapter 3 you learned you can brominate it, right? Br2, heat and light. This is old chapter 3 stuff, one of the first things you learned. And then a base takes off, so like we add a bromine, right? We add a bromine, and then we can eliminate the bromine with a strong base. So there's an E2 reaction, I don't know if you remember that. E2 reaction, and that makes the alkene. And then we can also, this is a net oxidation, and this is a net reduction. Okay, so we can go back and forth between an alkane and an alkene. All right. This is a huge thing. Huge thing is this concept of organometallic reagents, which are carbanions is a carbon with a negative charge. So one example is like an ethyl bromide or bromoethane reacting with magnesium. The magnesium just sneaks in between the carbon-bromine bond, and then it makes this thing called a Grignard reagent or a organomagnesium reagent. Okay, and that is essentially ethyl minus, ethyl dot minus. Extremely reactive, so it can go attack stuff. You can attack ketones and aldehydes and epoxides. So there's no mechanism for this. This is not an easy mechanism reaction. The other thing is that lithiums do the same exact thing. So the carbon-bromine bond can be converted into a carbon-lithium bond. Same idea, it's just it's not like the bromine is gone, okay? And this is also like a carbon with a negative charge. Extremely strong nucleophile and extremely strong base, all right? Cool. Okay, so an example of the use of these things. So if you have a Grignard reagent, like benzene CH2 MgBr, it can attack a ketone, and that makes, in the end, a tertiary alcohol. It makes a tertiary alcohol like this, okay? So this is a nucleophilic attack. You get essentially O minus MgBr plus, O minus MgBr plus. The O minus can grab a proton from like acid water or whatever, and then make the tertiary alcohol. This is an insanely useful method to make CC bonds. We made a CC bond. See the little blue squiggly? That's the bond we made, right? So we're going to build on that. You're going to do this. There's going to be a ton of new ways to do this in organic too. You got to know these, and you got to know the new ways, right? Okay. Another example. Here's a alkene CH2 MgBr reacting with an aldehyde. That makes a secondary alcohol, right? Reacting with an aldehyde will always make a secondary alcohol. Oh, what's the alkoxide? The alkoxide's the thing with the O minus, right? It's like the intermediate. Like this carbon attacks this carbon, right? Carbon attacks carbon. You get this thing called the alkoxide, which is the O minus thing, and then you protonate that, and you get the secondary alcohol. Okay. And the net effect is you make this little bond. So I use these little squiggly lines to to show the bond that we're making. All right. Okay. 1 second. Cool. And all right, what else? Here's another one. Now this is kind of near the end of organic, one. Anybody know what these are called? You can say in the chat. What's that thing called with the 3 carbon?
Epoxides.
Epoxide, you're right. Yeah, so epoxide is yet another thing that a Grignard can attack. So epoxides, right? So the aldehyde's an electrophile for Grignards. Epoxide is also, okay? So here is an example. The Grignard attacks the epoxide, opens it up, you make an alkoxide, grab the proton, and then the big thing, and you need to know this pretty well from organic 1, is where the squiggly line is relative to the OH, right? When we attack this aldehyde up top, the squiggly is right where the OH is. But when you attack an epoxide, it attacks the carbon, breaks open the epoxide, and look at where the squiggly is relative to the OH. It's on the next door carbon, right? It's a huge thing from organic 1 that you should know. Okay, chapter 9 when we talk about epoxides. Okay, cool. Another example, this idea of homologation. Homologation just means like add a carbon, add 2 carbons or something like that. So if I have a Grignard and I react with formaldehyde, it's a 1 carbon thing, right? And I get a 1 carbon homologation. I add a single carbon with an OH, right? That makes sense? Now, how could I do a 2 carbon homologation? Well, one way would be with a 2 carbon epoxide, right? So this carbon attacks the terminal carbon, opens it up, and now we've added 2 carbons. Look at where the squiggly is relative to the OH on the top. Look at where the squiggly is relative to the OH on the bottom, right? See the difference? Okay. Now these are alkene reactions, chapter 12. You're not required to know each of these in detail, but we were going to build on these because the alkyne chapter is going to be kind of like this alkene chapter, okay? And I'll look in the chat box to see if anybody knows any of these, what the reagents are. So like just pick the reagents. I'll start with an easy one, like alkene to 2 BRs. Anybody remember what the reagent is to add 2 BRs? I'll give you a hint. It's, there we go, BR2, yeah. Yeah, BR2, right? So that's an easy one. If you're adding a BR and an OH, it's a little different. It's BR2, and you add a, it's a water. Yeah, BR2 and a water, right? So these are 2 of the easier ones. This is kind of a weird one. It cleaves the bond. If the alkene gets cleaved, it gets snipped right in the middle. Cleave a bond. And anybody know? It's there we go. I see it. Yes, good. O3, ozonolysis. Yeah, O3, ozone, right? These ones you may or may not remember. There's like more. There's a little bit to know. That there's like the reagent and there's the workup, I guess. Anybody know the top one? We're going from an alkene to an alcohol. It's a metal. It's not. Well, anybody know the metal? It's mercuration. It's just a mercury one. This is HgOAC2. This one it's in chapter 12. It's one of the chapter 12 reactions. You're supposed to know. Okay. Now, again, like having good index cards from organic 1, you'd be easy to review these, right? You're going to see them again here and there, and I'm going to review them from time to time. This one. Oh yeah, top one. Is this Markovnikov or anti-Markovnikov? Top one. Markovnikov or anti-Markovnikov? I see, yeah, this is Markovnikov, right? The OH is going onto the least substituted carbon, right? The more substituted carbon, I'm sorry, right? The OH is going to the more substituted carbon. This one is anti-Markovnikov, right? Anybody remember this one? This is anti. It's BH3 hydroboration. Yeah, BH3. That's right. Yeah. This one, we're going from an alkene to an alkane. How do you do it? We're adding some H's, right? H2, yeah. Okay, and what about this one you may not remember? It's the two OHs. What is this? It's another weird metal. Weird transition metal. OSO4, yeah, OSO4, perfect, good. Okay, how about just adding what appears to be an H and a Br? You do that, an H and a Br, maybe you use HBr, good, good. And then this one is HBr plus a special additive. HBr and not palladium. Something that ends in IDE. No. HBr, it's, you put it on your wounds. If you cut your finger, peroxide, HBr peroxide. Okay, and then this, how do you make an epoxide? How do you make an epoxide? 5 letters. Oops. MCPBA. Yeah, that's right. MCPBA is the wonderful way to go from alkene to epoxide. Okay. The main thing you to really remember is if you have a basic nucleophile like a Grignard, it attacks from the least substituted side. Okay. All right. Yeah, we went through all of them. Good. There's some other rules for epoxides that we're not kind of organic one stuff though. I'm not going to really go into all the acidic openings of epoxides. All right. Here's a fun exercise. Good practice if you're rusty a little bit. I have the key on the website also, but you can kind of the main ones to practice are like attacking aldehydes, epoxides, ketones, etc. If you can get these, you're in pretty good shape in terms of your organic one knowledge. Okay. All right. Good. I'm not going to go through these, but you should be able to do them. The D2O is just like H2O, so it donates a deuterium. And carbon attacks deuterium. Kind of boring, actually. The other ones aren't very boring. They're actually very interesting, being able to build CC bonds. A couple more. And these are like kind of this retrosynthesis thing. You're going to be doing a ton of retrosynthesis, where you're kind of, building molecules, and you need to know, kind of like figure out what the piece is that's missing, right? I like to say, let's do it kind of algebraically, right? 3 carbons plus X is 4 carbons, right? 3 plus X is 4, X is 1, right? So figuring out what the piece is, and as a primary alcohol, that should be formaldehyde, right? This is a single carbon aldehyde. Here, it's like 2 plus X is 5, right? 1, 2, 3, 4, 5. 2 plus X is 5. X is equal to 3, and then you figure out tertiary alcohol, it should be ketone, right? Acetone. And the other trick is, another way to do this is draw a squiggly line. Like, there's your squiggly line, and then you figure out, okay, well, where's the squiggly line relative to the OH? Okay, it's right next to it, so that's a ketone, right? That kind of thing. Okay, so practice these. See if you can get these. The key is online also already. How about just bottom one? Okay, so bottom one. All right, look at the bottom here. I can't easily draw on the whiteboard because I don't have a whiteboard in front of me that I can use easily. But just think about this one. Where's the OH relative to the squiggly? Because the squiggly is right here, right? It's where the cyclopropane methyl thing is, right? And the question then would be, what is the functional group in the box? And I'll give you hints. It could be a ketone, it could be an aldehyde, it could be epoxide. Somebody said epoxide. Yeah, epoxide, right? It could totally be, that's what it is. If you have that skill down, you're doing pretty good from your organic one knowledge. And we're going to build on that, so you got to know this stuff. This is just another review of those alkene reactions. So see if you can get all these things, you're in good shape too. All right, cool. Are we done with this? We're done with this. Let's go into new material. Okay, did everybody see it? NMR? Okay, so I said there's 7 lectures. Not every lecture is like a full 75-minute lecture. Some of them are kind of short. I break them into 7 parts. Nuclear magnetic resonance is chapter 10 in the book. Okay, I stole this or borrowed it or adapted it from somebody else's lectures. Donald Pavia, who's a really famous professor at Western Washington University. I think he's retired now. And this was out of his textbook. But I changed these a lot, and it, you know, it doesn't totally match our textbook, but it's okay. In the end, if you read the textbook, follow this, you're going to get NMR. NMR is one of the coolest things in the world. Okay. I see the question, is the PowerPoint on the website? Yes, it is, but it's not on the iLearn, it's on the other one. It's on the public website. It's all on there. Okay, so the basis of NMR is that there's a concept called nuclear spin. So the nuclei of some atoms have this property called spin. So it's kind of like the nuclei are spinning. They're spinning around, right? Now we don't know if they actually spin. It's just kind of like it's easiest to think about this if we just assume they're spinning, and they can spin kind of one way, one direction or the other direction. Okay, and it's a property with a quantity that they can have two spins. You can have like proton, for example, H, hydrogen, can be +1/2 or it can be -1/2. All right, so each spin-active nucleus has a number of spins defined by this constant called the spin quantum number, okay? We'll call it I, essentially, right? And, okay, now not every nucleus does this. Proton does, and proton NMR is gonna be, really, really cool. And we're gonna, you know, it's gonna take a little while to learn it. We still got some theoretical stuff to learn before we do proton NMR. Okay. Here just shows some nuclei. We have proton. What's this one called? Anybody remember? 2H. This is 1H is proton. This is called deuterium, right? Deuterium is a different nuclei. Then we have C12, which is like almost all the carbon, right, that you're used to, and you know, in your body and everything. And then there's C13, and there's also N14. So there's this constant will define kind of the number of spin states, I guess. And the big thing about NMR is you need at least two, right? So proton has 2, deuterium has 3. C12 does not, it only has 1, so you can't actually do NMR on C12. But you can do NMR on C13. We'll talk about C13 NMR later. Most of what we're going to focus on now is initially is proton NMR, 1H. Okay, and there's 2 spin states. So the number of spin states is 2I + 1. You don't have to worry about, so a lot of this first lecture or two is very theoretical. Don't have to worry about knowing these formulas or whatever, right? Just follow along, all right? But you're not going to be quizzed on this. There's a lot of theory that you're not going to be quizzed on, okay? I'll tell you what you're quizzed on when we're ready for the quizzes. Okay, the most abundant isotope, C12, does not have spin. There's no spin property, okay? Which will be interesting. So, we'll get back to carbon NMR later, all right? Okay, so protons, let's talk about protons, 1H. Okay, so we have these 2 spin states. We call them +1/2, -1/2, there's 2 of them. The spin states, they generate a kind of a magnetic vector that aligns with a magnetic field. So we're gonna see magnetism shortly. The states are equivalent in the absence of magnetic field. So these have the same energy. They're basically, you got +1/2, -1/2, okay? But when we have a magnet, they're gonna align with the magnet, and one's gonna be higher energy and one's gonna be lower energy, okay? And that's gonna be the basis of NMR, the theoretical basis of it. Okay. All right, so resonance, the absorption of energy by the spinning nuclei. This is critical to how this all is all gonna work. So if we have a magnetic field, we measure magnetic fields with B0. It's like the strength of the magnetic field. Now they have, here's the magnet, north and south. Now they have, now you have 2 spin states. One's going to be aligned with the magnetic field, and the other's going to be kind of disaligned. And the disaligned one is higher energy, okay? When you have these 2 spin states with different energies, we're going to be able to kind of measure the difference between the energy. And that's going to basically tell us chemical structure in a bit. It's really cool. Okay. All right. So this kind of shows the same thing, right? That if I have a magnetic field and these 2 nuclei in these 2 spin states, I see a question. Are the PowerPoints only available in the 4 slide? Oh, are they only available in the 4 slides on 1 page format? I think so, but I may be able to help you out. If I might be able. I think on the website there, yeah, 4 pages on one. I may be able to do something different. Just email me if you're having trouble with that. Sorry about that. Okay, but anyway, so yeah, if we apply energy, and it's radio frequency energy, it's like light essentially. Uh, we can excite the aligned spin state to the unaligned spin state. It goes from the low energy to the high energy spin state, okay? And there's an energy difference, all right? So a lot of spectroscopy is based on this principle of absorbing light and promoting something from a low energy state to a high energy state. Okay, so this kind of shows it that the energy separation depends on the magnetic field strength. So you have a zero magnet, they're the same energy. As you start applying more and more magnet, then you get a bigger energy difference, okay? Now there's this equation that looks intimidating. It's not really intimidating. It's basically saying that the frequency of incoming radiation is dependent on a constant called the gyromagnetic ratio, or gamma, divided by 2 pi times the magnetic field strength. Or you could summarize this just by saying the frequency, well, this is a constant. Gyromagnetic ratio is a constant. The main thing is that the frequency is linearly dependent on the magnetic field strength, okay? So each nuclei has its own constant, okay? Each nuclei has its own gyromagnetic ratio. A lot of weird words, but that's one of them, all right? Okay, another effect of this strong magnetic field, when a spin-active nuclei, like a hydrogen, is placed in the field, it begins to precess. And that basically means it's spinning around the magnetic axis, okay? It spins around at a specific frequency. Okay, so you see it here. Here's the magnet, here's the nuclei, and it spins around at this frequency omega. Nuclei precesses at frequency omega in the magnetic field. Now, very interestingly, if you zap the nuclei with light of a specific frequency, now it could be 40 to 600 megahertz, it's like a radio frequency. If the frequency is the same as omega, the nuclei will absorb the energy, it'll absorb the energy and the spin will flip from one state to the other state. This is how it kind of goes from the low energy state to the high energy state by the absorption of radio frequency. Okay. Okay, so this is, like I said, I told you earlier that the gyromagnetic ratio is a constant, right? So proton has one, deuterium has its one, carbon C13 has its one. Okay, and then like I said, the frequency and the magnetic field strength are kind of just related, right? This is the Larmor Equation essentially, that the frequency is dependent on the magnetic field strength, but this is a constant. All right. Okay, good. Okay, so this is, we're going to actually see a real NMR here, and we're going to show you kind of like the old way to do it and the new way to do it. The old way is 1960s era, all right? And then we're going to show kind of the modern NMR way, all right? So, but this shows you how you do this, how it actually works in the machine, all right? You could probably find one of these on eBay, this old school one, for about $500. If you want your own NMR, put it in your garage. You can probably still buy these horrible old ones. Okay, so this is one way to do it. This is called a 60 megahertz NMR. Some community colleges still actually have these. You can use them in the organic lab class and just, you know, run your own NMRs. We actually have really good NMRs at SF State that research students actually use all the time. Okay, okay, so basically what you're doing is you have RF, radio frequency, you're generating RF. It's just a radio frequency generator. And then on the other side, you have a detector. You're applying RF and you're detecting, and then you have a recorder, like a chart recorder, okay? And then you have a magnet. That's basically it. That's an NMR. That's a whole NMR machine. You got a magnet, you apply RF, you absorb, you detect the absorbance of RF. That's it. That's all there is to it, okay? Doesn't work too well. This is the old way. The new way works infinitely better. I'll show you how that works. Oh yeah. This is kind of like a this is kind of how an NMR would look and how it's useful. Different types of protons precess at different rates in the same magnetic field. So you got a magnet, right? Here's a molecule with a benzene. What's the name of the functional group here? Name of the functional group. You guys should know your functional groups. It's a prereq.
Ketone.
Ketone. Yeah, you all. 2 people got it in the 80 students. Yeah, ketone. And so you got a benzene, you have a CH2, you have a ketone, you got a CH3. And each of these parts of the molecule will absorb at a different frequency, right? Okay, that is what makes this cool, because we're going to use this as a way to figure out chemical structure. We're a little far away from there, but we will, before you know it, I'm going to give you an NMR and say, figure out the structure. And you're going to be like, oh, okay, yeah, I'll figure out the structure. Okay, this is the basis of what we're doing, all right? So the magnetic field strength is scanned. We can scan the magnetic field strength. You know, we apply a single frequency, and then we're able to basically see these different types of protons, right? 3 different protons. You have the benzene ones, you got the CH2, you have the CH3, okay? What about the ketone? Can you see the ketone and proton NMR? Well, there's no protons on the ketone, so you can't see the ketone directly, right? Okay, right? Does that make sense? You can't directly see the ketone because it does not have any protons on it. But like an aldehyde, you can see. You can actually see an aldehyde in proton NMR. Okay. In a classic instrument, like I said, we basically would just increase B0. And you have a little chart recorder. This is really old school. And then you get a little printout that shows the signals as they come out. Okay? This is what it looks like. This is your first NMR. You're gonna have 1,000 more in this course, but this is a old school looking NMR of the phenylacetone. So the benzene corresponds to this kind of large peak. The CH2 is this kind of smaller peak, and then the CH3 is kind of this other peak, all right? Each proton comes at a different place, right? That's what, this is so cool, because each proton will come at a different location. If the proton types are different, you will see them at different places on the NMR spectrum, and that's what makes this so amazing. The x-axis, see the x-axis? It's 8, 7, 6, 5. We'll talk about that probably next lecture. ppm, yeah, and this ppm scale is a universal scale. So if you're taking NMR at SF State or taking NMR, you know, the other side of the world, everybody uses the ppm scale, and that allows you to, it's a universal x-axis measure. All right, be cool? Okay, so now let's talk about the modern instrumentation. This is called pulsed Fourier transform NMR. So everybody in the universe uses this now, FT-NMR, okay? So including the machines that we have. So I see a question. So what exactly do the higher peaks represent in comparison to the other lower ones? So a little hard to explain this second because we're still in very basic explanation mode. We'll explain why peaks come like at the left and why they come in the middle and why they come to the right, but we're not quite there yet. It's the next lecture, okay? For now, all you got to know is the different types of signals come at different places. Just, you know, give me a second, you know. Next lecture. We'll talk about these things. Higher peak, yeah. I think that answers your question. But you know, we're gonna have to. Some of this is gonna be next lecture, all right? Cool. And the other thing I'll tell you, electron withdrawing things like a carbon next to a chlorine or something, those will always shift things to the left. So electron withdrawing will always move things to the left. Okay, so, but yeah, we're gonna have to wait a little bit on that question. Okay, so what's this pulsed Fourier transform thing? So this is how we do NMR nowadays. The idea is rather than look at one single wavelength of RF, like 60 megahertz, what we do is we blast the sample with like every possible frequency. And then rather than scan the magnet, because the last one we were scanning the magnetic field strength, what we do is we just keep the magnet constant. Just keep the magnet constant and then blast all of the frequencies, boom, 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 boom. All of them get excited from the low frequency state to the high frequency, or low energy state to the high energy state. So everything gets excited, okay? And then you get something that looks really ugly. It's like, oh, each different proton kind of dissipates. You know, when you blast all of the different protons, they all dissipate. I was like, over time, it's like dissipate, 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 dissipate. So this is, it looks kind of ugly. You don't see that, you know, what we just saw a second ago, like you know, each peak has a, you know, each carbon, you know, has its own type of peaks. So this looks totally not useful, right? Well, what do you think happens if you add all these up? You get that. Do you think that looks great or not? It's actually, it doesn't really show you what you want to see. So how is this useful at all, right? You just see a bunch of dissipating lines. They're all averaged, okay? And this is called a time domain spectrum. It's time, it's right time. Left time goes to right time. Let's just go back a couple slides real quick. This is not time domain. This is frequency domain, right? These are basically different frequencies, right? This maybe looks useful to you, right? We have frequency 1, frequency 2, frequency 3, right? So the question is, how do we go from time domain to frequency domain? Anybody know? This is actually kind of an advanced math topic that we're just going to spend about 2 seconds talking about. But this is like something you would take like after calculus. I see the word integral. Integral is not quite what we want. Integral means kind of area under the curve, but that's not what we want. We want to go from time domain to frequency domain. And the answer is this thing called Fourier transform. It's a mathematical operation. And Fourier transform, or FT, right? Fourier transform, F-O-R-I-E-R, will convert a time domain spectrum to a frequency domain spectrum, okay? So it's a mathematical operation that resolves this. FID is this decaying signal, this decaying time domain signal into individual frequencies. You know, this is a very complicated math thing, but all we do is we press a button on the machine and it does it. Like it's a super complicated mathematical operation that we just press a button. We're like, all right, boink, and then it does it, right? And then you get your mixture of time domain frequency signals, and then you get a beautiful proton NMR with the frequency domain. Okay, we go from time domain to frequency domain, and that Fourier transform is just the operation that does that. All right. So let's compare the continuous wave, the old school method, with the Fourier transform method. So continuous wave, we scan the magnetic field from low field to high field, and then we scan the magnetic field and we just blast it with a single wavelength, 60 megahertz RF, 60 megahertz RF, right? There's a very slow technique and it's very unsensitive. So it takes several minutes. You only scan it once and you get a lot of noise. But this is what we had in the 1960s. How do we do it nowadays? So the pulsed Fourier transform method, we basically, what we can do is pulse over and over and over. We pulse, like pulse, 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 pulse. We can do this 100,000 times. So, and then each time you get less noise, you get more signal to noise, right? So we can pulse, 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 and then we take the Fourier transform, we average everything up press the button, get a Fourier transform, and you get a beautiful NMR, all right? So the pulse, it's all repeated, it's all automatic, it's super, super fast and easy, okay? Many repetitions can be done in a very short amount of time, and you get a beautiful NMR spectrum. So this is what we mean by that. Look at this, all right, so first pulse, horrible. Second pulse, or horrible. What if you do 10,000 pulses? You get a beautiful signal, okay? That's the beauty of Fourier transform NMR, okay? So I could take 1/10 of a milligram. I could take the tiniest little bit of stuff and just let it run overnight. Stick it in the machine, let it go overnight, and then I get a beautiful signal. If I take 1/10 of a milligram, the first scan is, you can't see anything, right? So it's like you get this improved signal to noise ratio. So everybody in the universe does this now, Fourier transform NMR. Okay, so what do they look like at SF state? We have two, well actually we got rid of the 300, so this is a little out of date. But this is the super old one, we got rid of it. I think we just threw it in the dumpster. It's a huge machine. These are the magnets, these are superconducting magnets. So this one we still have, it is actually broken right now. This one we got a couple years ago. Any guesses how much these cost? It's like 50 bucks or 100 bucks. What do you think? More than the car, less than the car? 10K, we see 10K, a lot. A couple million is a little overkill. The new one's about 500K, or 500,000, yeah. So yeah, this is a state-of-the-art, brand new one. We got about 5 years ago. So it's so cool. It's all robotic. So they look like water. Yeah, they totally look like water heaters. They do. But you have to put liquid nitrogen and liquid helium in them, and you can't let that go away. It'll destroy it. So we have to continuously be here. Even through the pandemic, we had people coming to refill these things because they will get destroyed if all the liquid nitrogen and helium goes away. Randomly, you might have heard of the somebody says I got one of those. Yeah. Randomly, you may have heard of the worldwide helium shortage, right? Helium is getting harder to get because it's going into the atmosphere, and we are going to be screwed when can't do NMR without helium. So eventually that's going to be a big problem, right? Anyway, so I think this is the end of the first lecture. I'm just going to start the second lecture. We have 15 minutes. We're not going to get too in depth into it. I just want to start a little bit. All right. So end of first lecture. Going into the second lecture. Okay. Somebody said integration in the chat earlier. So that's the first thing we're going to talk about is kind of like this area under curve. Okay, so somebody asked, what are the key points that we need to know from the first lecture? That's a hard question. I would say, what are the key points? Well, you're not going to be quizzed over any of that. So, I mean, it kind of depends on how much you want to know. The quizzable topics are a little bit later. And I know students hate when I say that. They're like, what do I need to know? What do I need to know? We're building right now, and we're kind of far away from anything that's going to be on a quiz. Okay, for now, just follow along. If you want the biggest take-home message from last lecture was that there's multiple spin states, and all we're doing is measuring the energy between them. That's the summary of the last lecture. Okay. All right. Integration is going to be the area under the curve, right? Okay. So here's back to our silly little spectrum, NMR Spectrum of Phenylacetone, right? We saw this. Recall that each type of proton comes at a different place, right? And it tells you kind of how many different types of hydrogen there are, right? Right? Or how many different, yeah, how many different types of hydrogen are there are? 3 peaks, 3 types of hydrogen. You got the benzene, you got the CH2, you got the CH3, right? That's kind of the first piece of information from an NMR. It's just like, how many different types of hydrogen do I have, right? Much more you can get out of it, but that's the first bit. So integration is the relative number of hydrogens, the relative number of hydrogens in a molecule, hydrogen type, and it's measured through integration. And integration as a verb could say the determination of the area under the peak. Okay. It's a relative. It's a relative amount of hydrogens. Integration is proportional to the number of hydrogens composing the peak, okay? So if we, this is the old school integration method, the old chart reader from the continuous wave. And in the old days, in the 60s, before they had computers and things like that we're used to, they would just plot it on a plotter, and you'd see these little squares, right? And the squares are basically the area under the curve, right? So I see 1, 2, 3, 4, 5 squares on this left peak, 2 squares in the middle peak, 3 squares. Well, that's interesting, because if I look at the molecule, how many CHs are in the benzene? Don't say 6, because there's not 6. There's how many CHs? It's a number right under 6. 1, 2, 3, 4, 5, right? There's 5 CHs, right? And then how many CHs are here? 2, right? How many CHs are here? There's 3. So if I can, div basically means kind of like, looking at, it's basically an estimation of the area. 5 to 2 to 3. Okay, 5 CHs, 2 CHs, 3 CHs. You can see that the area under the curve corresponds to the number of hydrogens in the benzene's part, the CH2 and the CH3. Okay, so these numbers are kind of like if I really carefully looked at, in the graph and kind of guesstimated, how much space is in these squares, I get around 55.5, 22 to 32.5, right? Okay. Now in the modern machines, this is all done for you. It's digital. It's all electronic. This is the old school way of doing it. But you can see that like 55 to 22 to 33 is roughly 5 to 2 to 3, right? It's a ratio. It's a ratio of the number of CHs in the molecule, okay? How do we know if there's a ring or alkene? Somebody said that privately. I'd say let's wait on that question. Alkenes are, a little bit different. There's a lot. Yeah, we have a lot to cover. So let's wait. Let's wait on that. All right, this second. Okay, this is what a modern one looks like. Look at that. It's beautiful, right? Very flat baseline, huge peak, huge peak, huge peak. The ppm scale is universal, which we'll talk about the ppm scale later. It's the x-axis, right? Same molecule. And now the thing is we get a digital number. It tells us the relative area. It's 58 to 21 to 33, okay? One of the things I'm gonna teach you, and you're gonna see over and over and over, is that peaks around the 2 to 1 region, the 1 to 2 region, are very often CH3, right? It's CH3s very often come around this 1 to 2 region, okay? Be some exceptions, but I see a peak of 2, and what I'm trying to do is like kind of take these numbers and then figure out the area, the relative number of hydrogens, right? So assuming that this is 3, it could be 3, it could be 6, it could be 9, right? It could be multiples of 3, around 2. Then if it's 3, 6, or 9 or something like that, I could just take that, divide it by 3, and be like, okay, well, I get 11.3, right? And that would be the integration that corresponds to a single CH, right? If this is typically 3, well, take this divided by 3. Oh, okay, 11.3 is a single CH. And now, given that, I can look at these numbers and figure out the relative number of hydrogens under them, right? And so take these numbers, like 21.215 divided by 11.3, and I get 1.9, and take this number divided by 11.3 and get 5. Okay, now I see, oh, it's roughly 5 to 2 to 3, okay? So this is a trick you sometimes have to do, and I'm gonna give you some practice on this later. Let's not worry too much about it, okay? But that's the idea of, the basic idea of integration. It tells you the relative number of protons under a signal. If you're a little confused right now, don't worry about it. We're still early on in this stuff, all right? Take the lowest number always. Well, okay, so somebody asks, take the lowest number always. So if you're not given anything I'm looking around the 1 to 2 region for maybe a CH3 that might help you. Don't worry about it right now. We're going to see more examples in a bit. Okay. Just keep that in the back of your mind. Round 1 to 2, CH3. Maybe 2 CH3s, or whatever. Okay. Okay. So accounting for hydrogen atoms in the molecule. We're going to show another example. We're going to show another example now. All right. So what about this molecule? How many different types of protons are there? It's a small number. How many different types of protons are there? I see left CH2, right? And I have the middle CH2 and the right CH3. Yes, three kinds of protons, right? 1, 2, 3, right? 3. How many NMR signals am I going to see? I'll give you a hint. It's the same number, 3. 1 for that one, 1 for that one, 1 for that one, right? What did I say about chlorine? Is it going to be kind of to the left or the right? The CH2 next to chlorine, left or right? Ooh, it's actually the left. Okay. Again, don't worry too much. If you're not getting some of this, we're going to reiterate this a bunch. It's going to be the left. The CH2Cl is going to be, its electron is drawing, it will be the left. Okay. Okay, so here we are, and here's our NMR spectrum. And what did I say? What's the left one? That's probably the CH2Cl. Okay, and then we have basically 3 signals. 1, 2, 3, and in this case they actually match. This one correspond to the left, middle, and the right. We will get into that more later in this lecture. We're going to stop in a second. So, but what I'm trying to show is the integration. What is the integration expected of these 3 signals? There's a CH2, a CH2, and a CH3. It should be something to something to something, right? 2 to 2 to 3, right? 2 to 2 to 3. Okay. What's this little red curve? See the red curve? Okay. Students have a little trouble with this, but it's we'll probably close on this topic. Look at this distance between the bottom and where my mouse is going. See that distance? And let's look at this distance. What's this distance? And this distance. Do you see 2 to 2 to 3? Because that's what I'm trying to have you see, right? This distance is about, this is given this molecule, this looks like 2 to 2 to 3, right? Medium-ish, slightly larger. The ratios are similar graphically. Yeah, they totally are. And this red curve, the red curve is the integration, is the area under the curve, right? The red curve is the area under the curve, right? So from here to here, see that distance? It's a CH2, next Cl. This distance is a CH2. What about this distance? Well, that's another CH2. Ah, they're the same. See that distance and this distance, how they're the same? And I'm not going from, I'm not going from the baseline. I'm going from here to there. See this distance? See that distance? Distance right there? How this is the same as this? That's what you're trying to see right now. So this distance to this distance, if this is 2, well, that has to be 2, right? That is absolutely true. If this is 2, this has to be 2. And if this is 2 and this is slightly larger, well, that's probably going to be 3, right? Okay. There's going to be some tricks where, if I give you the molecular formula, this really helps. And that's what we're going to start with next time, is if I give you the molecular formula, this really helps. I don't give here I give you the structure. So yeah, how many CHs are there total? There's like 1, 2, 3, 4, 5, 6, 7, right? 7, right? C7, 1, 2, 3, 4, 5, 6, 7, right? 7 protons. Okay, so whatever I come up with has to equal 7. And I just told you it's 2 to 2 to 3, 7, right? 2 to 2 to 3. It helps that I give you the structure. We're not quite there where I don't give you the structure yet. That's going to be really hard, and we got a long way to go, a long journey, right? But if I say 7 and I say account for those 7 protons, it should be pretty easy to say, oh yeah, 2 plus 2 plus 3. Okay, we're at the end of class, and I think I just got to stop, and we're going to continue Zoom on Thursday. We all cool? You don't have to totally get every little bit of this yet. Some of this is going to be confusing, and then it's just going to get a little more clear. I guess we'll just stop now. Okay, wait. I see somebody says, could it be 3 plus 3 plus 1? That's a great question. Okay, somebody said, could it be 3 plus 3 plus 1? Well, given the line, how could you say this is 3, that is 1? The line wouldn't make sense, right? Great question, though. Could this be 3 to 3 to 1? Well, I don't see 3 to 3 to 1 because this is bigger, right? Larger space. Whatever this is, it's got to be bigger than that, right? Are we cool? Okay, I'm going to stop the lecture. If anybody wants to keep talking, I'm going to just, yeah. If I'll be here, but yeah, I don't know. Hopefully this was not too boring. It's gonna be fun. You're gonna love this. NMR is gonna be the coolest thing you learn.
Thank you. Have a good day.
Okay. All right, guys. See ya. Office hours opening right away. Well, okay. The question was, will my office hours be starting right away? Well, I guess our first office hour will be on Friday. So, but if you have a question, email me or something, right? We cool?
Thank you.
Thank you.
All right. Thank
Appreciate
you.
it.
All right.
Thank you.
Cool. Oh, first quiz. Well, okay, so the first quiz is probably going to be a very silly one, like and multi-day. It'll be like you have 4 days to do it, and I'm probably going to post it on like next Tuesday. And it'll be like, you know, anybody could do it without any thought. There's no studying. It's going to be like, look up a molecule in Wikipedia and draw it. I just need you to practice the submission process. Okay, so you need to learn how to submit. Do you memorize Larmor? No, Larmor's not. No, don't memorize that. Yeah, and you don't have to memorize anything because it's all open note anyway, right? There's nothing to memorize. I would say the Larmor equation is really boring. Yeah. Any other questions? Will that red line be given? That's a good question. Will the red line be given or derived? Most likely, it'll even be easier. I'm going to just say, hey, it's 2 to 2 to 3. So when we actually get to the real problems, you know, which are far away from now, I'm probably just not even, I'm going to make it as easy as possible. I'm just going to say, hey, it's 2 to 2 to 3. Okay, but you're going to see the red line a couple more times. So just, you know, be ready for it. You know, it's a little challenging when you got to figure it out, but it's very easy if you know how many hydrogens there are, right? If you know it's 7, you should be able to look at this. If I say 7, and you should say, oh, well, it's 2 to 2 to 3. And remember, the other thing is that, remember what comes around 1? What always only comes around 1? 3s. It could be 3, it could be 6, it could be 9, right? And it can't be 6 or 9. That would be impossible because there's 7 protons. How could you have 6 and then have these, right? That wouldn't make sense. So 3 is the only possible thing that would make sense if this is 7, right? If I tell you 7 protons, you have to think, how do I get 7? 2 to 2 to 3, right? Right, that makes sense. Is in NMR, will I ask you to come up with a structure? Absolutely, and that is going to be fun, and we're going to have so much practice of that, but that's literally lecture number 7. So we're so far away from that really fun stuff. We have a lot of fundamentals to get through. Lecture 7, we're going to do like 20 examples of here's an NMR and what's the structure. And if you want to look now, go for it. It's all on there. It might be hard, but if you can do it now, then you're set. But we're still, you know, we're not quite there yet. Yeah, it's a lot of fundamental stuff I got to teach first. But and we're gonna do that in every chapter of the book. Amines, ketones, aldehydes, esters. You're gonna have so much fun doing NMR. You're gonna love it. So, all right, we're good.
Yeah, thank you.
Okay, see you guys. Bye-bye.
Bye, Professor.